So, we have been working out the example. Now, it is lecture 13 on module 1 on dynamics of ocean structures course. In this module, we are discussing about the fundamental structural dynamics. We are solving some numerical examples. We have been continuing with this problem of a fixed beam, which we did partially yesterday. Let us say I have a fixed beam with variable moment of inertia. So, this is I and this is 2I, and let us say the length of the segment is L by 2 each, and let us say this is point C, and we are going to use the moment distribution method or the moment distribution technique to actually find the equivalent stiffness of the section. So, we already found out the distribution factors. I think this was 0.33 and this was 0.67. So, the sum should be always 1, however may be the number of members meeting at a joint. So, now we want to find out the force which is responsible to cause unit deflection at this point, because this is a point where my W is hanging. So, I know already that W is equal to mg. So, if I know W, I can always find m, and for a single degree idealized system, if I know K equivalent of this, I can easily find the natural frequency of vibration caused to this beam because of the suspended load W. When you have got both ends fixed and you are suspending a load, it is expected that the member will bend, therefore looking for a bending stiffness, which is in the earlier example we looked about the axial stiffness AE by L. In this case we will look at EI by L, but it is not going to be EI by L because there are two I's and two segments and support conditions are different. Therefore, we have to find out K equivalent in this particular problem. So, we will try to revive what we did yesterday. If I got a support, if the support settles by delta, we already said if this is delta, we already said this will invoke a moment which is from the first principles of mechanics, it is 6E delta by L square, where this is L, and of course, the member is having the property as EI, and it settles by delta L. So, the significance of marking the arrow direction of the moment is associated to how you are displacing the joint. Okay, we discussed this yesterday. So, the same amount will get transferred here 6E delta by L square. Since we are interested in finding the equivalent stiffness of the member, we will always say I want to find the force for unit deflection, and therefore, delta is going to be unity in the whole exercise. So, I am trying to write down these values for both these pieces separately here. Let us say this is one piece, this is another piece. So, you know this is going to settle down because that is what I am trying to do. The displacement should be given in the direction of the load, therefore, I will have a moment of this order on this order. Essentially, this is going to be 6E delta by L square. So, if I write this 6E of I, because I is here and L square, I say it is L by 2 the whole square, which will give me 6EI by L square, which will 24 EI by L square. So, I write here 24 EI by L square, same 24 EI by L square. Now, the right hand segment, that is CB, again the left hand support of this part is settling down. So, therefore, the arrow direction is going to be lift it up, similarly clockwise here. So, this is again going to be 6E delta by L square. So, I write the value here 6E of 2I by L by 2 the whole square, which is 6E of 2I of 4 by L square. So, 48. And this is going to be 48 EI by L square. This is also 48 EI by L square. I want to do a moment distribution for this particular member ACB in a conventional form, which we know. So, let us say member AB, sorry, AC, CA, CB and BC. This is joint C, this is joint A, this is joint B. So, this is joint, this is member, this is a conventional table what we generally make for a moment distribution technique. So, then I write the distribution factors. Distribution factors always worked out only for a joint which has got more than 2 members, at least 2. So, now A and B does not have more than 2 members, therefore, there is no distribution factor for A and B. For C there are 2 members, therefore, this is 0.33 and this is 0.67, which we already worked out yesterday as K by sigma K. Now, we also find a value called fixed end moments. This is not finite element method, this is fixed end moments. Let us just expand this. It is fixed end moments, briefly abbreviated as, let us say, FE. Okay. So, let us have a sign convention. We will make sign convention clockwise as positive. So, you all know that this is C, this is A and this is B. So, I can call this as MCA, this as MAC, this as MCB and this as MBC. The first letter corresponds to the joint, the second letter corresponds to the next joint. That is how the nomenclature is written. Start from here, this is anti-clockwise, so minus. I only write the value, I will have a multiplier of EI by L square outside, because it is going to be common for all, I will only write the number. Similarly, here again anti-clockwise, so minus 24. Similarly, CB, it is of course clockwise, so plus 48, and BC again clockwise, plus 48. So, the minus and plus corresponds to the sign convention what you have assumed. You can assume the other way also, okay, does not matter whether clockwise is negative or positive, does not matter, but you should follow a sign convention through and through constantly. So, you will know the problem how it is solved. Now, obviously, you will see that at joint C there are unbalanced moments, okay, it is not balanced. So, I have to balance this. That is the principle of moment distribution. First you balance the unbalanced moment, then you distribute it, that is what is called moment distribution method. Okay. Now, how do we balance this? It is very easy, you must know the procedure, but anyway for people who do not know this, let us quickly explain them. Appreciate that we are trying to follow the principle of structural mechanics applied onto dynamics to find out K equivalence. Okay. We are not interested in finding the moment distribution BMD, SFD for this problem, no. We are interested to know what is the natural frequency of the system, it is vibrating, that is very important. So, I want to know the equivalent stiffness K, so I am using delta is equal to 1 here. So, I am trying to get the force responsible for this. So, now the positive number is higher, therefore, the balance will be negative, okay. Positive number is higher, therefore, the balance is negative all the time, okay. Now, if I say this is x, this x value will be actually equal to the difference of this, which is 24, no sign here because sign is already written here, okay, no sign here 24, the difference of these two, algebraic difference of these two multiplied by the corresponding df, okay. How much is this? So, I will write it here minus 7 point, be louder, 92, okay. Obviously, one can find this value also, it is nothing but the difference of these two, again 24 multiplied by 0.67, 16.08, because this sum should make it as the difference of these two in terms of its sign also, okay. So, it is 24 now, okay, 17 plus 7, 24, right. Once you do this, you try to carry over this, I call this as carryover. Now, the carryover is nothing but the same sign, half of this, okay. So, it is 3.96 and this is 8.04. Okay. So, this is called one cycle, one balance, one carrier is one cycle. Let us make a total now. So, while totaling, you will not total this is only a factor not to be total, you will total this and this, okay. So, it is minus 31.92, and you will total this plus 48 and minus 16. So, plus 31.92, and of course, plus 48 minus 8. So, plus 39.06, right, and this is going to be minus 27.96. Now, you see, now this has been balanced, therefore, I can write this as final moments. They are not final moments because we have got some values here. They are final moments because the joint is balanced. Now, if you have more than one joint in one cycle, all the joints may not be balanced. So, you keep on doing this cycle until they are balanced, but moment distribution has a limitation. You can modify this method within 3 cycles, you can balance it. Okay, we are not looking into the description here, that is all in dynamics class, mechanics class, we will forget about that. My job is again taking back these forces to find the stiffness for unit deflection, that is the problem here. Okay, that is what I am, let us not deviate from that at all. If you have any doubt on further joints are there, how will you distribute, please read a classical mechanics book, you will understand that. Okay, now my job stops here, that yes, I have got the forces, let me check whether the answers are okay. 9/6, right? Okay, I will remove this. Let us draw these values graphically in the same problem here. So, this is A, this is B, and this point is C. So, we already know clockwise is positive. So, I get anti-clockwise at AC. So, it is negative, therefore, it is anti-clockwise, which is 27.96. The convention is you must write the value at the head of the arrow. Okay, that is the convention. If you are not written, you please follow that. The convention is you must write the magnitude at the head of the arrow. That is the right way of writing. You cannot write anywhere you want, written here. There is no need to put plus minus here. The sign convention says clockwise is positive. So, the value is negative, therefore, it is anti-clockwise. If you have doubt in whether clockwise is an anti-clockwise direction, please see your watch if you are wearing one. Now, you see the other one is again negative. Let us say this is again anti-clockwise because it is 31.92. And this is clockwise 31.92. So, it is balanced, again positive 39.96. Okay. I want to get the forces now, I am having the moments. So, with this I can plot the bending moment diagram, but I want to plot the shear force, actually I want the forces. It is very interesting. Let us draw the segment separately and say this is 27.96 and this is 31.92. So, now you see this particular segment of the beam has an unbalanced moment of the sum, which is 59.88. Right. So, when I got an unbalanced moment of anti-clockwise 59.88, it should be balanced by a couple which is opposite. Now, this couple should be clockwise, which will balance this, and couple is nothing but force into distance. I know the distance is L by 2, I want to find the force. So, this is simple 59.88 okay, by L by 2 okay, and EI by L square is already there, you see here, is already there, because these numbers do not make any meaning except that multiplier of EI by L square. Okay. So, I should say this as 59.88 into 2 EI by L cube. Is it 119.76? How much? So, I will write down 119.76 EI by L cube. This will also be same 119.76 EI by L cube. Okay. Let us do the second part. So, this is clockwise of 31.92, this is clockwise of 39.96. So, it has got an unbalanced value of clockwise of Okay. So, this will get balanced by a couple of this order, because clockwise is unbalanced, therefore, the couple will be anti-clockwise. Okay. This value is going to be 71.88 by L by 2 of EI by L square. Now, commonly people make a mistake here, they say that this value of beam is having I, this value of beam has 2I, should I multiply 2I here? Please do not get confused, this is a multiplier drawn from the table. This 2I and I chakra has been already included in these values. Please see the calculations back again. Okay. So, no 2I here, the multiplier is just borrowed from the table, that is all. Okay. So, this is going to be how much? 143.76 EI by L cube, 143.76 EI by L. Okay. Now, I am bothered about this particular point. Why? This is the point where I have given unit deflection. So, the moment I say the deflection is unity, the force at this point will be equal to my stiffness directly. Okay. So, my K value will be directly equal to sum of these two. You will see automatically the force is happening in the same direction as that of the displacement. Okay. Suppose by mistake if you have gone these arrows up, you have done somewhere wrong. So, how much is the total? 119.76 plus 143.76. So many EI by L cube. How much?
263.5.
Yeah. Okay, I can put K bar indicates equivalent stiffness. So, I know M, which is nothing but W by G, I can find omega n square root. You can also check the units of K, let us see EI by L cube, Newton per mm square or Newton per meter square, whatever units you want to fix. I meter to the power 4 meter cube. This will automatically give you Newton per meter, which is a classical unit for stiffness. Okay. So, mass is already in kg, you will find omega in radians per second automatically, which is an equivalent stiffness for this problem. Okay. So, it is very easy demonstration of using a classical moment distribution method to find out frequency of vibration of this beam. Now, in this there is an idealization that we have already said that mass will be lumped at a point where you want to measure the frequency or the degree of freedom. But it is not necessary always that mass should be lumped at a point always where the degree of freedom is measured. Okay, there are examples I will show you in the next class where we will violate this and see what happens to a matrix. Okay. Any doubt here? Okay, we will take it understood, we will move to the next problem. Are we an example 4? 5. We will have another classical problem here. I have got 2 degrees of freedom problem. Let us say I have a cantilever beam where I have 1 degree of displacement or degree of freedom as downward, I call them as x degree of freedom, the other is tip rotation, which is theta. Now, interestingly, if you had only 1 degree, you could say the stiffness would be for unit deflection can be 3a by L cube something, standard equations are there. If it is only rotation, you can still find. If there are both available here, what would be the equivalent stiffness of this member? Okay. So, for this there are 2 methods. One easiest method is derive lateral stiffness matrix or lateral stiffness term, which I saw K bar. You have to derive this. We will derive this quickly, how it can be done. Very easy to derive, remember, that is horizontal. We can easily derive this. Let us say I have, we all know standard equation in matrix algebra is K multiplied by displacement will give me the force, okay, because Newton per meter, meter Newton. Okay. I am using the same algorithm here. K matrix. So, x theta, x theta. This is a capital K in sense it is a full matrix. The elements are small k, row first, column next, row first, column next, row first, column next, row first, column next. Okay. In a given matrix 1 2 3 1 2 3, if you want to read this member it will be k 2 2, if you want to read this member it 3 3 and so on. Okay. Similarly, this one k 1 3, row first, column next, that is how we generally read a matrix. Okay. Multiplied by displacement x and displacement theta will give me Px and P theta, that is force in x and theta degrees of freedom. Now, let us expand this. Kxx dx plus Kx theta d theta is Px, equation 1, K theta x dx plus K theta theta d theta is P theta, equation 2. Equation 1 has d theta, I can evaluate d theta from equation 2, substitute in 1. So, evaluate d theta from equation 2. Let us do that. So, d theta will be now equal to P theta minus K theta x dx of K theta theta pre multiplied inverse, that is the order. Okay. So, substitute 3 in 1, this is 3 in 1, this is 1. So, Kxx dx plus Kx theta of K theta theta inverse of P theta minus K theta x dx is Px. Okay. Let us equate this further. Kxx dx minus Kx theta K theta theta inverse K theta x of dx, the first term, this and this, first term, of course, plus Kx theta K theta theta inverse P theta is Px. Okay. Now, these two terms are related to dx, this term is related to d theta, which I eliminated already. Okay. D theta is not there here. Okay. Yeah. So, let us write the first term, Kxx minus Kx theta K theta theta inverse K theta x of dx, okay, plus is equal to Px. It is very easy to remember this equation. I will tell you how. See, I will write it here just for your understanding. I will not look at that, I will write it here. It is very easy to remember this equation. Equation may look longer, you can easily remember this, the order what I am telling you, because in mathematics or in dynamics you have to remember a lot of shortcuts. It is easy for you to, it is a life savior. Okay. Now, I want to write Kxx minus Kx theta K theta theta inverse K k theta x of dx. So, it is very easy, k x x, k theta theta, theta theta, k x. You can easily remember this like this. Okay. There is a compatibility, k x x will match with k x x. This entire equation is called k bar, which is called lateral stiffness matrix in engineering. I will demonstrate the advantage of this with a problem. Okay, I will demonstrate this advantage with a problem. You will appreciate that this matrix will be very handy if you can derive this quickly for a given problem. This is called k bar, where k bar is called lateral stiffness matrix. So, we will demonstrate this. I will take up a problem whose degrees of freedom are 1 and 2. 1 and 2 are the degrees of freedom. Okay. EIL. EIL. These are the properties of the member. Okay. Now, I know m of this member at this point. If I know k bar of this member, I can find omega n. That is the whole clue. Okay. If one alone is acting as a single degree, you can find k bar, k. If 2 alone is acting as a single degree, you can find k. But I am converting the 2 degree problem into a single degree by using k equivalent. Okay. And both the degrees of freedom are of a different nature. One is translational, other is rotational. Okay. If both are translational, you can add them as series or parallel. Both are rotational, you can sum them up algebraically. But if they are of different nature, you have to derive an equivalent stiffness, which is from this equation. Okay. Let us see what k x x is. Let us see first what is k I j. K I j in general is force in the ith degree for unit displacement given in jth degree, keeping all other degrees of freedom constrained. That is a classical definition for stiffness coefficient k I j. Okay. Let us apply this equation for this problem. My k bar should be k11 minus k12 k22 inverse of k21. Am I right? See, kx xx, kx theta, theta theta inverse, theta x. So, k11, k12, 22 inverse, 21. So, 22, 22, 1. It is easy to write and remember also. Okay. So, now for this problem I must know k11, k12, k21 and k22. Rather, I must know the individual stiffness matrix of the whole system. Then I can convert this into a single value k bar. That is why it is called sometimes equivalent stiffness matrix. It will be a single value now. The whole matrix will be converted to a single value. You will see how it is. Okay. So, I want to find k11, k12, etc. Let us see what it is. So, for a given problem, if this is 1 and this is 2, so to find K matrix, which will be a 2 by 2 matrix, why? The degrees of freedom are 2, it will be a square matrix of 2 by 2. So, the matrix will look like this: K11, K12, K21, K2, row first, column second, row first, column second. Okay, we write like this. Now, I want to know these individual coefficients of this matrix. So, what should I do? To derive the individual coefficients, I must always apply unit deflection at the specific direction and get the forces, that is K. Okay. If I give unit deflection at the first degree, keeping the other degree restrained, that is the beam or the member moves only along one, whereas 2 no movement. Why, you may ask me? That is a constraint available in the definition itself. Okay. So, I must give displacement only along one. Let us forget about 2, find the forces. So, what I will get? I will get K11 and K21. It means for unit deflection along 1, I get forces in 1 and 2. Therefore, stiffness matrix is always derived column wise. It is always derived column wise. Okay. On the other hand, flexibility matrix will be reversed, will be derived row wise, because they are inverse to each other. So, I will get the first column if I give unit displacement along 1. If I give unit rotation along 2, I will get the second column. On the other hand, I will get all the 4 coefficients. If I get all the 4 coefficients individually, plug them in this equation, get a single value which is equivalent stiffness matrix of a member which has got 2 degrees of freedom, but with 1 k. So, 1 m, 1 k, 1 omega. Okay, it is easy to solve. Okay. See, before solving the problem, try to understand what you are trying to do in the problem. Otherwise, this will look only as a demonstration. You will never be able to apply this idea in any of your problems in your research. Okay. So, do not look these problems as simple magical solutions applied on the board. No, you must understand how we are proceeding with the problem, why we are doing it. If I have this difference matrix of 2 by 2, which is a 2 degree of freedom system, I will have to solve this problem to find omega by matrix method. Now, I am trying to make it easy, I am converting this into equivalent stiffness. If I had 2 spring series, 2 springs parallel, I know how to do that, but in this case the degrees of freedom are different in nature. Okay, so, I cannot apply those standard logics to find k equivalent so easily, so I am using this method. Okay. So, let us derive this. So, I must give unit deflection here, delta as 1. Okay. So, this will have a value which we just now saw. Okay. This will also have a value. It is going to be 24 EI delta by L square, delta is 1 in this case, sorry 6 EI by L square, 6 EI delta by L square, delta is 1 in this case. Similarly, this is also going to be 6 EI delta by L square, delta is okay. So, 6 and 6 are 12, therefore, I will have a couple which is going to be 12 EI by L cube. Okay. Let us look only at this node. Okay. This force is in the direction of 1. Okay. Therefore, this will be equal to K11. This force is in the direction of 2, but opposite in nature, because 2 is clockwise in the original problem, whereas I have got a value of anti-clockwise. So, I should say this is equal to K21 with a negative sign. It means my K11 is 12 EI by L cube, my K21 is minus 6 EI by L square. Okay. Okay. I am deriving column wise. Let me move to the second one. I want to give unit rotation. So, hold the stick and give unit rotation, it will move like this. Okay. So, this will invoke a moment which is equal to 4 EI theta by L, classical mechanics. Okay. And this will be equal to 2 EI theta by L. Now, this has got an unbalanced couple of 6 EI delta by L or 6 EI theta by L. So, this will have a couple which is 6 EI by L square, and this is also 6 EI by L square. Okay. Forget about this part. Look here, there are two forces, one is this and other is this. One is this upward, but the degree of freedom one is downward. Therefore, this will be equal to K12 Y2, because I have given unit displacement in the second degree. Okay. And this value will be equal to K22. So, I get the second column. So, K12 is going to be 6a by L square, but it is in the upward, whereas the original degree of freedom is in downward, therefore minus 6ei by L square, and K22 is clockwise, my 2 is also clockwise, so plus 4ei by L. Okay. This is my K matrix. I have all the values K12 first row second column, first row second column, K12 I have, K22 I have, I can take an inverse of that, K21 I have, substitute them, substitute and get K bar. Let us do K bar. I will rub this, okay, I will do it here. K bar is going to be K11 minus K12, K22 inverse, K21. So, let us substitute them, which is 12 ei by L cube minus K12 first row second column. So, minus 6 ei by L square, K22 inverse, so L by 4 ei and K21 second row first column minus 6a by L square. So, 12a by L cube minus 9a by L cube, am I right? Right. So, 3a by L. K bar. Okay. You can also check the units A by L cube, Newton per square meter, meter 4, meter cube, Newton per meter, which is as same as the units of K bar, number 1. Number 2, for a problem of 2 degree, K should be actually a matrix of 2 by 2, whereas you are converting the whole matrix of 2 by 2 into a single value, which is nothing but 3a by L cube. Now, you got a single value, that is why it is called equivalence difference matrix. Okay. So, I use this method to find out that. Now, if I know K bar, if I know m, I can easily find omega n for this problem. So, it is demonstrated with an example like this. We will also do another example to demonstrate this in a frame problem, because now jacket structures are frame structures. We will take up this in a jacket problem and see how this can be demonstrated for a frame problem. So, B, this was A, I will demonstrate with one more problem. Let us say I got a frame like this, EIL and EIL. The frame has got 2 degrees of freedom. One is a tip displacement, which is 1, other is a lateral displacement, which is 2. Now, first let us appreciate this problem, how this is different from that. There are many differences. Let us see the classical differences first. The first classical difference is a beam problem, it is a frame problem. The second classical difference is both the degrees of freedom are measured at the same point there, but it is not so here. Okay. But still for this problem also I can find K bar, which is K11 minus K12, K22 inverse, K21. I can easily find this. So, I must get first the full K matrix, okay, for this. So, to get K matrix, I must apply unit deflection at 1 degree, get the forces in 1 and 2. I must get unit displacement at 2 degree, get the forces 2 and 1, get the matrix, substitute here, find K bar, which will be an equivalent single value. Now, if you know the mass of the system, I can get omega n quickly. So, there are some cases where you will be requested to or required to find out the fundamental mode of vibration and frequency for a given problem before you proceed with the design of the system. Okay. So, these are all equivalent methods by which you can easily find omega n within minutes. Okay. This is a classical matrix method used by different leading software to compare the answers. Okay. Softwares also check the answers, it is not that they do only by one method, codings are written for different methods. If any one method fails, the other method will be enabled automatically in the subroutine to find the solution, they check. This is one method by which every software checks whether the omega n or k is correct. Okay, it is very easy, it is matrix method. I am using the same equation, same algorithm for solving this problem. Okay. Let us pick up this and apply the same algorithm here and see how I can derive the stiffness matrix. Okay. So, let us give unit displacement in this degree. Okay. So, the frame will deflect like this. So, I require a moment which is 6 E delta by L square. I am writing it here because there is no space on the head. Also have same, and this will now anti-clockwise, clockwise 6 E I by L square and 3 E I. So, now this has got a couple of 9 E A by L square. So, it has got to be balanced, which will be 9 E I by L cube. Okay. And this has got a couple of 12 E A by L square, it has got to be balanced. By a clockwise couple, and this value will be equal to 12 E A by L. So, obviously, this value is going to be K11, because why it is because K11? This is the force in the first degree because of displacement given in the first degree. Now, the force in the second degree I want, it is lateral. So, I have to look at this value. You may ask me, say this also lateral, but this is at this node, this is at the other node. So, at this node, this value which will be equal to K, the node is 2, but displacement given in 1, therefore, it is 2. Force in second degree because of displacement given in first degree. This is force in first degree, displacement given in first degree. Kij, force in first degree or ith degree because of displacement given in jth degree, keeping all other degrees constrained, and that displacement is unity, that is how you get stiffness. Okay. Therefore, it is unity, in whole equation delta goes away, there is no delta here, you see. The delta is unity, I have removed it. Similarly, let us give displacement of 1 . So, this will invoke 6 E I by L square, 6 E I by L square, and this anti-clockwise or clockwise of 6 E I by L square and 3 E I by L square. Here people generally get a fundamental doubt. At this point, people generally think it is a free hand or a overhang. So, why there is a moment there? The moment should be 0 actually, because it is a free hang, no, overhang. In matrix method of structural analysis, all members are always considered as stiff ends at both. In matrix method of structural analysis, in stiffness method, every member you take, member 1, member 2, member n, it is always considered by default both the ends of the members are fixed, okay, then you have got to release them. That is how it is 3 ABL square. The second doubt what people will get is, sir, when we transferred 6 has become 3 here, but when we transferred 6 has become 6 here. Why? If the displacement is transferred, it is full. Okay. So, this has got to be clearly, these are two doubts what generally will get, and the major doubt what people will get is how to mark these arrow directions. Okay. That doubt has got to be explained many number of times, you must know, and of course, very silly doubt is how will you mark the arrow directions of the couple, that you must understand physically. Okay. If it is clockwise, anti-clockwise moment, clockwise couple and so on. So, you must remember strongly how the rotations takes place. Okay. Now, this is clockwise of 9. So, I will get couple of this style which is anti-clockwise, which is 9 EI by LQ, 9 EI by LQ, and here this is again 12. So, I will get the direction of this type, because this is anti-clockwise, this couple will be clockwise, which will be 12 EI by LQ, 12 EI by LQ. So, this will be actually equal to K displacement given in 2, force in 1. So, K1 2, and this value will be actually equal to displacement given in 2, force also in 2, K2 2. So, I got both the values. Let me write the stiffness matrix here, K matrix, K11 12 EI by LQ. You can always take EI by LQ out 12, let us say plus 12. Why positive? This force is acting down, displacement degree is also down. And the second one is here. So, this force is towards the left, whereas the degree is towards the right, therefore, minus 9. Look at the second figure, I am looking for the second column. So, second displacement. So, I am looking here K1 2, the force is up, displacement is down. So, minus, and second degree here, force is towards right, displacement towards right. So, plus 12. Okay. So, I have to substitute K bar is K11 minus K12, K22 inverse, K21. I have all the values, K11 I have, K12, 2, 2, 21 inverse I have. I can easily find K bar. Can you give me what is the value of K bar? How much? 21 by 4, okay, yeah, 5.25, okay. Well, it is very easy to find. Unit compatibility, this will give you Newton per meter. I have converted the problem of 2 degree to a single value. If I know m, I can find omega n easily. So, two examples A and B are demonstrated for finding out equivalent lateral stiffness matrix, which is K bar, which is a very important advantage in application of dynamics for finding out fundamental frequencies if you are idealizing the problem into an equivalent single degree problem. This will always required in many cases. Okay. Any doubts? Okay. We are also opening up the exams maybe in another couple of days, and my request to all the viewers is you must register for the exams. There are many questions people are asking, I am not able to solve the tutorial, will I be eliminated for the exam? Tutorials are not connected to eligibility for you to appear for the exam, they are separate. Okay. But if you do not do tutorials sincerely, exams will be difficult. So, my request to all of you who are listening to this course is please register for the exam. Centers are all over India, and in fact people are registering it from abroad. You will also have an online provision of taking the exam. There is no difficulty. It is very throwaway price. So, you will be given a certificate. You will also given a relative score. Now, the current capacity of people registered for this course is very high. So, instead of getting a denominator as a class of 50 or 60 or 100, now you are talking about a 4-digit number. you will know actually where are you placed in international scenario as far as dynamics is concerned. It is a good opportunity for your self learning also. So, please register for the exam once it is open, look for the website of NPTEL. Thank you.